Okay, so this interesting event today continues. So welcome to the Vienna Gödel Lecture of the Faculty of Informatics of TU Wien 2024. I'm Stefan Seider. I'm hosting this event. The Vienna Gödel Lectures was inaugurated in 2013 with the great Donald Knuth. And since then, we had every year excellent, prominent, I would say the top of computer scientists here to give the Vienna Gödel Lecture. And today, this continues with a great speaker, Daniela Rus. But before I give her a proper introduction, we have two welcome addresses. One by our rector, Jens Schneider, and then from our Dean of the Faculty of Informatics, Gerti Kappel. And please, may I hand over the mic?
Thank you. Yeah. Thank you very much, everybody. And I want to keep it short because I think everybody is very curious about Daniela's talk. First of all, I just want to stress 20 years Faculty of Informatics. I think this needs an applause right now. Of course, when I saw your logo, Dean Kappel, I was a little bit afraid because now it's very small here, but maybe you can show this 20 years logo. The 20 years logo reminded me of one important or very interesting film. I don't know if you remember The Shining. The Shining. So I was thinking, what is happening with the informatics? Stanley Kubrick's The Shining, it's a horror film. But I just learned by the founding dean, where is he? The founding dean, we just talked. And he told me that at the beginning it was said, I now say it in German, then translate later. Die Informatik ist das schlimme Kind der Mathematik. So the informatics is the black sheep of the family or the bad child that couldn't be taught to behave correctly. So das schlimme Kind. And I just learned that originally it was founded already interdisciplinary right from the beginning, that it was not a spin-off of the mathematics. It was also not a spin-off of the electrical and information technology, but somehow it was a mix of everything, which I like because I'm convinced that this interdisciplinary research we do at TU Wien is really important to solve the challenges of the future. What are some USPs from my perspective being new here when I heard informatics? Of course, first of all, one has to stress, I think this is now at the moment the most successful faculty of TU Wien. I think both, yes? So it's number of people, students, research, innovation, and international reputation, which is important for us. We just talked about it, that we need to be much better in what we can do, because in international context, I think the competences that you have here at the faculty are really compatible and comparable to the best schools all over the world. From my perspective, there are some things that come to my mind being here new. Of course, it's logic. First of all, I always hear informatics TU Wien is logic. So it's precision, it's hard at the same time, and also sometimes maybe unforgiving, because it's so logic that it's unforgiving, but it's also philosophical. If you see now, this lecture is Gödel Lecture, and it's powerful, it's strengths. And when I came here and somehow fell in love with TU Wien more than about 2 years ago, I was asking myself, why is it? I think it's also this context that we have in Vienna and having this opportunity to have this multi-diverse surrounding of Vienna and all the people here in TU Wien, but also in Vienna. And it's also because I have a special feeling that we have a USP with our young academics and our students. I think they are special, and I believe we should concentrate in the future more about our USP as universities, which are the students and which are the young academics. And especially here, I believe also Informatics did a really good job to promote the best people to take their career here. I want to end my little welcome with a quote from Marc Aurel, which is more than almost 2,000 years old. He said, the universe is change. Our life is what our thoughts make it. And I think this perfectly fits to your faculty. So thank you for this day today. I'm really curious also about the lecture. And I hope that the next 20 years will be as successful as the first 20 years.
You already have heard me, ladies and gentlemen, and there's not much to add to our rector. But perhaps one thing, you know, I know Georg almost since ever. Also not since 50 years, but at least since 88 when he started here. And he's really one of the most charming persons in the world. But when he's talking about females, one has the feeling he gets a problem. So when he was talking about Troch, yeah, he said, there was also Troch. You know, the people of my generation, we remember Troch. She was the first female professor at TU Wien, and she was studying and teaching and researching simulation. So applause, yes, for Troch. She's not here. Yeah, I can tell you she's not here. We missed it, but I will tell her because I know her by chance also privately. Next to that, at least he remembered Ina Wagner. And she was the first female professor in computer science in '85. And great that you are here, Ina. I don't know where I see you, but somewhere you are here. And last but not least, thank you to our former rector, Sabine Seidler. She told me she will be here, but I think I don't see her now, because it's really up partly to her that we have now 50% of female assistant professors, and we are increasing at associate and full professor level. So it's totally different to 45 years ago when I started here. I won't say the future is female, but it is at least diverse. Of course, by chance, this fits greatly that we have Daniela Rus today as our lecturer, our Gödel lecturer. And I can really tell you the most important thing, as I already said in the beginning, is people. Yeah? And everywhere are great people. There are great people in the most poorest part of the world, and there are the great people at the east and the west coast of Austria. The only difference is talent is everywhere, but not opportunities. And our goal and our responsibility is to provide opportunities to everybody. So thank you, Daniela, that you are here, and I hand over to Stefan.
Thank you for these two very empowering addresses. Now, before I introduce the speaker, at the end of the talk, there will be time for question and answers. And in addition to just raising your hand and ask the question in the microphone, actually, we prefer if you could type in your question. We have this, you can find the link on this card. Also, people following us via Zoom can also, of course, ask the questions, and you can also upvote questions. So hopefully this way we will, because we might not have time for all the questions, so we can ask the most interesting question, or those where most people find them interesting. And my colleague Chua Chen will then read some of these upvoted questions. Okay, but now technical stuff aside, now to this the great part of this event is, of course, the talk and the speaker. So I'm very happy that we could win Daniela Rus to give this Vienna Gödel Lecture. So Daniela is a professor at MIT, and she directs there the computer science and artificial intelligence lab, which is not a tiny thing. It's, I think, more than 125 faculty and more than 1,500 people working there. So it's really a huge thing. And in addition, there is also the MIT Toyota Joint Research Lab, where also Daniela directs this lab. So she must be very busy, and therefore we are even more happy that she could squeeze us into her calendar. So Daniela received many awards and honors, and but for the sake of time, I just mention maybe one early career award. That's the MacArthur Award, which is also known as the Genius Award. So I think I always, when I hear somebody got the MacArthur, I thought, oh, that's a different category of people. Yeah, Daniela's research, of course, it's on robotics, and more in particular, her research pushes the boundaries of what robots can do and what they can achieve by enhancing the machine's reasoning, learning, and adaptability in human-centric environments. And she creates user-friendly interfaces that foster a natural and intuitive interaction between humans and robots. And she also develops innovative tools to rapidly design and produce next-generation robots. And so her research is very impactful in a multitude of sectors, such as, and I have to read this long list: transportation, manufacturing, agriculture, construction, environmental monitoring, underwater exploration, smart cities, healthcare, and even domestic tasks like cooking. Okay, now I'm looking forward to, I think, a very interesting talk entitled Physical AI, Promises and Challenges. Please join me welcoming Professor Daniela Rus.
Thank you. Thank you very much for this very generous introduction. It is truly an honor to be here at the university at TU Vienna. This university has been such a hub for scientific and technical advances that are making an impact, an important impact today. And so I'm inspired by the groundbreaking discovery of the Doppler effect, which I use all the time in my underwater work. And of course, this was done here at the university by Christian Doppler. And the pioneering work of Heinz Zemanek on one of Europe's first computers continues to inspire us for pushing the boundaries of what is possible today. These are foundational works that continue to make a huge impact. Now, while preparing this talk, I have been reflecting upon Kurt Gödel, the namesake of our gathering today. And I learned that he came to Vienna exactly 100 years ago in 1924. And he's made so many important contributions, and in particular, his incompleteness theorems, which he developed here in Vienna nearly a century ago, around 1930s, 1931, have fundamentally altered our understanding of mathematical systems by demonstrating that within any given system, there are true statements that cannot be proven. And this profound insight into the limitations of formal systems resonates deeply with the challenges faced in machine learning today. And so just as Gödel revealed the inherent limits of mathematical frameworks, we also strive to build AI systems that can understand and navigate the complexities of human language and thought. And we have a long way to go, as you have seen in the previous lecture, in the previous wonderful lecture. And so my journey in this field started some years ago when I was a student studying computer science at Cornell University. And I went to Cornell University to build computers that interact with the physical world. At the time, we had some very early robots. They were primarily big industrial robot arms. And one day, a group of us decided to make a present for our professor's birthday. We wanted to program our robot arm to cut a piece of cake for him. And so we took some duct tape, we attached a big butcher knife to the robot, and we spent all night writing the software. And it was the robot was very carefully programmed to do these kinds of motions, because that's how you programmed robots back then. But the next day, disaster. We had programmed our robot for a soft, round sponge cake. And the guy who went to pick up the cake came back with a rectangular, hard ice cream cake. But we had invited all the department there, so we thought, okay, we got to see what happens. So the robot attempted to cut the cake and went like this. And then disaster, the robot started flailing and it nearly destroyed the cake. But our professor was delighted anyway. He calmly pushed the red button to stop the robot and declared the erratic behavior of the machine a control singularity, which is a technical term in robotics. Now, I was very disappointed, but I learned a very important lesson for someone aiming to build machines that interact with the physical world. I learned that the physical world, with its physical laws and imprecisions, is a far more demanding space than the digital world. And today at MIT, I continue to think very hard about this. Now, today in the field of computing, we have two largely separate fields. We have artificial intelligence and robotics. And these days, AI is amazing us with its decision-making and learning. But AI remains confined inside computers in the digital world. On the other hand, we have robots that have a physical presence and the ability to execute tasks. But the robots execute pre-programmed tasks, and they're not intelligent. In fact, if you have seen the extraordinary Boston Dynamics robots that dance with Mick Jagger and look extraordinary, I want to tell you, these robots are not intelligent. They are pre-programmed. It takes months to choreograph, to get the robots to do a 3-minute dance sequence. And so the interesting thing is that the separation between AI and robots is beginning to change. Because AI is about to break free from the confines of 2D computer screen interactions and enter a vibrant 3D physical reality. And in my lab and in my research group, we're fusing the digital intelligence of machines with the mechanical prowess of robots. Now, if we move AI from the digital world into the physical world, we will make machines more intelligent. We will create physical intelligence, and we will begin to build what I like to think of as the next breakthrough, and what I call physical intelligence. And so you can think about physical intelligence as our ability to take AI's power to understand digital text, images, and all kinds of online information, and use that to make real-world machines smarter. And so this means that AI can help pre-program robots do their tasks better by using knowledge from data. So with physical intelligence, AI doesn't just reside inside our computers, but it walks, rolls, flies, and interacts with us in ways that are truly extraordinary. Now, just imagine robot helpers anywhere and everywhere in your world. For instance, at the supermarket, the one on the left could help you carry a box, and others help clean the windows and stock the shelves. There are so many options that we have when we bring AI into the physical world. But to make it work, we have a lot of challenges we need to overcome. And in particular, we need to change how AI thinks, how machines are designed, and how they learn. So let me tell you a little bit about these three topics. Okay. So for physical machine, we need to put the AI brain on the body of the machine. This is our soft robot fish that has explored the oceans. And you can see the size of the fish comparable to the human hand. Well, today's AI uses server farms that do not fit on the robot. So we have to think about that. Additionally, today's AI makes mistakes. For example, this is an AI perception system of a self-driving car, and this AI system fails to detect the pedestrians crossing the crosswalk. So this is a problem because if you don't see the pedestrians, you're going to run them over. And so for physical intelligence, we need small brains, small AI models that do not make mistakes. So how do we get there? Well, we are tackling these challenges in collaboration with Professor Radu Grosu and his group here at the Technical University in Vienna, using inspiration from the natural world, from a worm called C. elegans. And so now, in stark contrast with the billions of neurons we have in the human brain, C. elegans has a very happy life with only 302 neurons. And so this, and the other interesting thing is that biologists understand how these neurons work. And so we asked ourselves, can we make machines that use fewer neurons and that are model on the biological work? And so here's the idea. Why not use the math of the worm to build a new class of AI? And we've called this class of AI liquid networks. Let me show you an example. So liquid networks are compact and explainable models as compared to today's solutions. And liquid networks came about as the collaboration with Radu and his students how to stay in lane. And we started by using traditional AI models, namely deep neural networks. And so you can see the car is doing pretty well, is driving well on a new road. But now let me show you what's happening under the hood. And it is impossible to correlate the activity of these neurons with the behavior of the car. And so furthermore, if you look at the lower left corner here, you see where in the image the AI engine looks in order to make decisions. And you can see that, first of all, the image is very noisy, and the solution looks at the bushes and the trees on the side of the road. In other words, it looks at the context of the task. And so that's not how humans drive. People look at the road. People look at the road horizon and the edges of the road, not at the bushes and trees on the side of the road. Now, let's compare this with our worm-inspired liquid network solution for self-driving cars. And so here you can see that we can drive a car using only 19 liquid neurons rather than tens of thousands of deep neural network, deep artificial neurons. And furthermore, look at the attention map. It's the road horizon and the sides of the road on the horizon. And so this is really exciting. Also, because the models are so much smaller, we can understand how they make decisions. In fact, we can extract Prolog programs that explain exactly how they make decisions. So I think that there will be a resurgence of Prolog very soon. Okay, so how is this performance possible? Well, in most traditional AI solutions, the artificial neuron is an on-off computational unit. It takes some numbers, it adds them up, it applies some basic math, and the neuron puts out a 0 or a 1, and that's how it passes along the result. And this becomes complicated because it is happening across thousands of neurons. Liquid networks use fewer neurons, but each one does more complex math. And so if you look at the math, it's not so simple. We use differential equations to model the artificial synapse and the neural computation. And these equations are inspired by what biologists have determined is happening in the neurons of worms. And we also wire the neurons differently in order to capture loops and in order to capture the more of the biology of the natural world. So these liquid networks are actually an example of continuous time neural networks. And in continuous time neural networks, the network is defined by a function f that is defining a series of differential equations. And these models are a type of temporal neural networks, which includes other models like RNNs and neural ODEs and CTRNNs. And so there's a whole class of continuous time neural networks. Liquid networks are one of them, and they're defined by this very particular equation, this very particular mathematics we add. And so why need this particular mathematics? Well, continuous time neural networks can be used for many tasks. For example, this is a standard task. It's called a half-cheetah locomotion. And this is a task machine learning experts use to measure the performance of their algorithms. And so, we can use many different kinds of differential equations for the neural formulation. And we get a very elegant solution for the task. But despite the elegant formulation, when we apply the continuous time networks, the existing continuous time networks, to even simpler tasks, we see that they do not perform better in practice than a simple discrete time neural network like LSTM. And so this, to us, pose the question of, can we build a model that preserves the beautiful properties of continuous time machine learning solutions, but also has good performance? And so, in fact, our solution is in that category here. The lower the number, the better. So how did we arrive to our solution? Well, our solution is composed of two insights. So first, we start with a well-behaved state space model in order to increase the stability of the neuron during learning. And then we introduce non-linearities over the synaptic connections in order to increase the expressivity of the model. And when you take these two equations and you plug them into each other, you get the equation that defines the liquid time neuron. And so what's interesting here is that, in fact, this differential equation, in this differential equation, the time constant actually depends on x of t, which is one reason why we have such good properties. Okay, this is it about math. No more equations, I promise. So, so here you can see again the comparison between our solution with our equations and CNNs, CTRNNs, and LSTMs. And you can see that the attention of all these other models is very fuzzy. It's very all over the place. So you really wonder, do they really understand the task, or are they more about the context of the task? Well, we can prove a lot of interesting things about liquid networks. We can prove that they are stable and bounded. We can prove that they are universal approximators. We can prove that they are actually dynamic causal models. And we also can show that they generalize very well, and they're very expressive. So, that's really exciting, because that means we have a model that has some of the properties we long to have in machine learning. Okay, let me go back. It's the same equations. It's not new ones. So let's go back to the equations, because we're also looking for a performant model. And if you have a system where you actually have to use numerical integrators to solve the system, that consumes a lot of energy. So we may get nice properties, but if the energy cost remains high, we might question the benefits of the model. Well, interestingly, the equation that defines the computation of the neuron has a closed form approximation, which is here. It's very hairy, but the point is that it allows us to skip the numerical integrators. So now we have a machine learning solution that is very compact. Instead of, in fact, it's thousands of times more compact than a traditional solution. And we no longer need numerical integrators. The computation at each neuron is a kind of a straightforward function. So it's interesting, because these these simple changes we've made, inside the neuron yield phenomenal results. Most neural networks are frozen after training. That means if you take them and you apply them to tasks in the wild, they cannot continue to learn. If you want a different model, you have to wait for the next release. But these solutions are adaptive after training based on the inputs that they see. And here's an example. So we trained traditional AI and liquid networks to find things in the woods, using essentially data like what you see in this video. So I don't know why this is not playing. So let's see again. Okay, now it's playing. So we basically have, all right, we have videos that are not labeled and that can, that basically show a drone going to a unique red object. So using this kind of input, we designed an end-to-end control network, and then we created different architectures for this network. Now, let me go back here to our data. All the data was collected during the summer. So the background of this of the task is green leaves. Then we tried to use our solution during the fall, when the background looks very different. And so here's a standard deep neural network solution that is utterly confused. If you look at the attention map, it doesn't really know where to go, because now the background is different. However, the liquid network solution is very clear on what the task is. The attention is very focused on the object and on the task. So you see, so we trained in the summer. Today's neural network solutions would not be able to do the task with a different background. But here is liquid networks having no problem in the fall when the background is very different. In fact, the solution works really well in the winter when there are no leaves and when the scene is essentially black lines instead of green texture. And we can extend this even to sorry, I don't know what that, I guess there was the robot noise. Let me see if I can take it down. All right, we don't need robot noises today. Oh, okay, let me try again. Okay, so so now without noise. So here you can see an urban setting where there are a lot of possible distractions, but somehow the robot knows exactly where to go. And another example that shows how if you put the object of interest in an urban setting, the LSTM solution gets confused by the windows, but the liquid network solution does not. And you can even take the same model trained in the woods with a static object, and you can make it work in a dynamic setting where now the object is moving and the environment looks completely different from the data that we have experimented with. So this is very encouraging. We've applied liquid networks to other domains. And so we work with surgeons at Massachusetts General Hospital. One of the tasks we're studying has to do with predicting the next phase of the surgery. And in this case, we're looking at gallbladder surgery. And we have about 20 videos that were manually annotated by surgeons with a phase. And we tried a wide range of models for doing this kind of phase prediction, phase recognition, which, by the way, is very important because in the operating room, it's very important to be precise with bringing the tools for the doctor. And here you see that the green line at the very end on the rightmost side of the graph, it has the best performance, but it's also the smallest. It's also the kind of solution that we can actually put in computers in hospitals. Now, we talked about transformers in the previous session. We've also tried liquid networks with other standard data sets that are used to evaluate transformers. In general, we get 123% improved performance over the other methods. And in particular, we have some interesting data sets. So in text sentiment analysis, which now uses liquid networks with language, with words, and in information retrieval, we get on the order of 10–11% improvement, which is quite a lot. And in on medical time series data for vital signs, we get accuracy improvement of 33 times over transformers. And so I think this is a very exciting approach to machine learning. And what's interesting is that this method is physics-based. It uses physics, it uses dynamical systems rather than straight-up statistical models that do next-word prediction. And because of this formulation, we can then use tools from the control theory literature and from the dynamical systems literature to understand how these systems work. Now, the ability of liquid networks to handle text as well as sensor information, sensor data, gives us another benefit. And so if we go back to control tasks in the physical world, for instance, in driving, we can begin to consider whether language is an important part of intelligence. We can begin to ask, rather than consider an intelligent machine as the connection between perception and action, what happens if we bring language into that loop? So now it's not just perception and action, but it's perception, language, and action. And what we find is that with language, we can elevate the level of reasoning of the machine. So instead of always thinking about XYZ coordinates and geometry and really the physicality of the world, we can begin to think about concepts that can be specified in words. And so the way we're approaching this idea is by building multimodal versions of our AI brains that connect visual information with textual description of that information. And what we have to do is to build a model that aligns the perceptual features with the language features. And so it gets a little bit hairy here, but essentially we find a set of features that are relevant to our task, and then we curate a set of textual features that can be swapped in and out, and ultimately we simulate the image features by sensibly swapping in target features. So what does this mean? This means that I can take a let's say a driving model, and I can train it to avoid deer. So I provide data, I provide video data and say, okay, this is how you drive around deer. And then in language, I can say, okay, now you know how to avoid deer. Also avoid people and trees and benches and buildings and anything you want expressed in words. And I actually don't have to provide all this data. I don't have to provide videos of people and trees and benches. I can simply swap in the concept using text, and all of a sudden, I am then able to reason about what is happening in the scene using higher level abstract concepts. So here's an example where we trained in simulation. Sorry, it's a little bit unclear. It's a little bit fuzzy, but we trained in one scenario to avoid cars, and then we immediately were able to transfer without any further training to transfer so that we don't kill Bambi. And we can also go from a rural summer dry day to many other different types of scenes without any additional training. And here are a few more examples. So this is pretty exciting because I really think we have so much opportunity to think about what does language bring to our intelligent machines, and how important is language to intelligence and to our abstract reasoning. So we have some numerical results. Here you can see the results from running all these different types of scenarios, these kinds of generalizations without our method and with our method. And you can see that by bringing the language in, we do so much better in this out of distribution scenario. So I am very excited about this method and this way forward, and I'm really so grateful to have an opportunity to work on this with Radu and his former students and his current students. And next time I come, hopefully we have even more results. But so we continue to work on how we can get the brains of machines to work better. But we also are thinking about what kinds of machines can run these really magical brains. And so by now, I imagine most of you are familiar with using text-to-image systems. Most of you might have created images using DALL-E or other text-to-image systems. So we wanted to do text-to-robot. But not using today's solutions, because the solutions are statistics-based and they do not understand physics and they do not understand common sense reasoning, the common laws. And when you do text to image, you can create fantastical images, which are okay for the digital world, but the fantastical mechanism that doesn't do the right thing is not okay for the digital world. So here's the solution that we developed. So we developed a solution that guides the design process. It's an AI solution that guides the design process by checking and simulating the physical constraints. So you start with a simple language prompt. For instance, please design a robot that can walk forward. And our system will generate the design, including the shape, the materials, where it's hard, where it's soft, the sensors and the program required to control this mechanism, and also the fabrication files to make it. And so we have a kind of a stability diffusion based approach that generates these designs. Once the designs get generated, we actually check to see if they meet the physical constraints. And we use the results from the simulation as a interesting, it's a tabletop with legs, but then every leg is kind of like a worm. So it's kind of a weird design we have developed to do text to robot. Now we can also do image to robot. And this photo of a bunny can be transformed by a piece of software, an algorithm, into a cuddly robotic bunny. And here's how it works. We take the bunny and we use an algorithm to compute a 3D representation. And then we slice this 3D representation, we unfold it, and then we print the unfolded layers, we fold them back up, we string some motors and sensors, we write some code for controlling the motors, and we get the bunny you see in this video. And this approach can be used to make almost anything from a photo. So you know, using AI to do text to robot or image to robot is important because we can drastically reduce the time to design and prototype new products. And this is allowing for faster innovation cycles. And we can use this approach to design almost anything. So we can design innovative grippers. Here are a bunch of grippers that, that we have designed using this approach. And here's another one that has different grasping properties. So this one is more delicate. The other one was stronger. And we can design small things. We can design big things. We can bring almost anything to life. And so, for instance, here's an example of generating a robotic version of the Sydney Opera House. So if the Sydney Opera House were a robot, this is what it would look like. We can also design completely new types of robots. And so this other application is inspired by medicine. In fact, I learned from my students that every year thousands of people swallow accidentally button batteries. And button batteries are actually dangerous because they create holes in the stomach tissue in a very, very short amount of time. So like within an hour, a button battery is fully immersed inside the stomach. I didn't really believe it. And then my students bought a piece of ham, put a button battery on it, and I saw that within an hour, the battery was completely submerged. And so the way this is taken care of now is with a surgical procedure. So we asked ourselves, can we build a little robot that could be packaged like a pill and that you could swallow, and then the robot could go pick up the battery and eliminate it through the digestive system. And so we built a folded robot that can squeeze like an accordion. Then we put it in a capsule, in a pill mold. We pour water over it. And the patient swallows, at least the vision is that the patient would swallow this ice pill with a robot embedded in it. And when the pill gets into the stomach, the ice melts, the robot deploys. And then, because the robot has a tiny magnet embedded in it, we can use an external controllable magnetic field, kind of like an fMRI, like an MRI machine, and we can drive the robot to the pill to pick it up. And so here is a research experiment with a simulated stomach. Here's our pill that is being driven by a magnetic field to the battery. It picks it up and it eliminates it. And by the way, this robot is made out of food. The body of the robot is made out of sausage casing. So the robot could even stay inside the body to be digested. In fact, after the pill is eliminated, we imagine that we may have another robot that could come in to patch a wound or develop or deliver medicine in a very precise way, and could just sit there and get digested. And so this technology can be used to obtain tissue samples, to stop bleeding, or to get a better view inside our bodies. The opportunities when we broaden our view of what a robot is, what we make it out of, what the robot looks like, the opportunities are so exciting. And then when you can bring in computational methods to automatically design these machines according to task, the possibilities for creating intelligent machines that help with a variety of tasks is so extraordinary. And so we continue to work on this task. But now that we have we have a new way to get machines to think, and we have automated ways to design machines. The question is, can we make these machines intelligent? Can we get them to learn? Because if we could get these machines to learn, we would really move to physical intelligence. And this is the third aspect of intelligence. So what we've observed is that these machines can learn from humans using data about how humans do tasks. Now, there are several research laboratories around the world who are looking at how to get machine learning models to learn physical tasks. Most of this works use digital video data, but video data does not capture the dynamic nature of tasks, and this limits the ability to learn and execute them accurately. So in our lab, we created a kitchen environment, and in this kitchen environment, we instrument people with sensors, and we collect a lot of data about how people execute tasks. And so, for instance, here you can see a close-up of one of our subjects that has a muscle sensor. And we then write machine learning solutions to recognize which high-level activity is the human doing based on feedback from these wearable sensors. So we have a lot of sensors who record pose, muscle, even gaze information when people perform kitchen tasks. And then we use this data to learn from humans how to do tasks, because video alone does not capture what needs to happen in this really complex physical interaction. And so we have this data, and then we use this data to learn how to get robots to perform those tasks. And the end result is machines that are less mechanistic, machines that move with more grace and agility, as well as adapt and learn. Physical intelligence. Work is at the very beginning. We have not fully explored the scope of our data, but it's very exciting to think about what can be done when you have such rich data sets. So the ability to turn photos and words into functional machines, coupled with using liquid networks to create powerful brains for these machines, is extraordinarily exciting, because it means we can build almost anything we imagine. We can bring to life almost any object in the physical world. So today's AI has a ceiling. It needs server farms, it's not sustainable, it makes inexplicable mistakes. And what I'd like is to think about what happens next, what can come next beyond these very powerful but digitally centric solutions. Because I believe that when AI comes into the physical world, we will see incredible breakthroughs and benefits. We will have personal assistants that optimize our routines and anticipate our tasks. We will have bespoke machines that help us at work, and robots that will delight us in our spare time. The promise of physical intelligence is really to transcend our human limitations with capabilities that extend our reach, amplify our strength, and grant us the ability to interact with the world in ways we have only dreamed of. But to get there, we have a long way to go. There are a number of technical challenges that we need to address. And in particular, on the AI side, we have to continue to think about the data side of AI. How can we do machine learning that uses less data? We also have to think about data quality. How can we have AI solutions that do not have bias and that respect the privacy of the people who provide the data? How to have energy efficient solutions for AI that are sustainable and that do not cost a lot of money and that can run on enterprise computers and on the small computers on edge devices like our robots. In safety critical applications like in medicine or in robotics, we cannot have a solution that we do not understand. We have to address the interpretability aspect of AI. And we have to make AI solutions more robust and more capable of thinking deeply. We also have societal challenges around the deployment of AI. The spread of AI will make our lives easier, but many of the tasks that AI can do, many of the roles it can play, could potentially displace work done by humans today. So how do we anticipate and respond to the potential economic inequality that this would create? Also, the lack of interpretability and the dependence on data can lead to significant issues around privacy. We need to address these issues, and we need to develop the kind of framework for using AI for the greater good. Now, the spread of, we're in an election year. The spread of misinformation is extraordinarily important, especially all around the world, but we are faced with it in the United States. And so this remains a big concern because as deep fakes get better and more widespread, this problem will become more urgent. And it's important that we address it. And so there are so many really important issues whose solutions will be at the intersection of technical ideas and also policy and business ideas. The exciting thing is that as a community, we have named all these problems, and now we're working hard to find solutions. And I am convinced that we will have amazing solutions. And with these amazing solutions, we will have extraordinary opportunities in the future. Just imagine waking up enabled by your personal assistant that figures out the optimal time for you to wake up and organizes and collects everything you need for the day. Here comes the robot with your outfit. Now, as you walk to your office by a store, you can imagine intelligent store windows that display your picture with all the latest fashions. And inside stores, you have systems that can measure you precisely so that all the clothing and the shoes that get built for you end up being bespoke, end up being done just for you, just for what you need. And in fact, even the clothes that we wear could become robots in their own right. For instance, you could program them to change color, or you could embed sensors that keep track of many of your vital signs. And then at work, inside the intelligent boardroom, you can have temperature that gets adjusted automatically, and holographic images of your colleagues appear so that you can jointly design the new products. In this case, they are designing a flying car. I aspire to never be stuck in traffic again, so flying cars is the answer. So that we will have flying cars, and these new cars will be connected with the IT infrastructure, and they will know your needs, so that they can tell you, for example, that you can buy plants that you have been wanting nearby, and they will even compute a small detour for you. And back at home, as you take your first ride on a bike, adaptable wheels appear and disappear according to your skill level. Robots help planting, garbage bins take themselves out, and well, robots can deliver the purchases of the day. And after a good day, when it's time for a bedtime story, which allows you to enter the story and interact with a dragon, you will have much more, much richer ways of fantasizing and interacting and thinking about what the world could be. Well, these are some of the ideas for how the work we're doing in our field of computer science can change how we live. Yet developing and understanding machine intelligence is teaching us that we have so much left to learn about technology and about ourselves. We have a lot of questions that need to be answered sooner rather than later, before AI plays out without a guiding hand. So I believe that we remain responsible for this planet and for everything living on it. And we have to consider that as we think about how we advance technology. Now, I am convinced that we can harness their power to ensure a better future for humanity and for the planet. And we can help build this future together. And I want to invite all of you, the students and the faculty at the University of Vienna, to think bold thoughts about how the world can be better with computation, with the kinds of machines we can now begin to develop. And I think this is a wonderful time for us to think about this. 20 years of informatics at the University of Vienna has created so much benefit and so many important results. What will the next 20 years look like? I look forward to joining you in 20 years to see what the world looks like. So happy birthday, Faculty of Informatics. Thank you very much. So I'm told that you can scan this QR code and you can send some questions.
Wow, thank you very much. This was really interesting. Wow, now I don't know, Chihua, are there already questions? Then maybe let's start with an online question.
Okay, so can you hear me? Yeah, thanks a lot for the very interesting talk. And I think this is a very necessary topic that we are facing in the future. But let me start with several questions. I think the first question would be about the liquid neural networks. So how do you ensure that liquid neural networks provide explainable and transparent decisions, particularly when combining complex data from images and language? Can you expand on prologue resurgence?
Yes, I would like to direct you to a paper about interpretability in small networks. It turns out that if the model is small, you can extract a decision tree that can be mapped onto a logic program, and that logic program actually explains how the model reaches decisions.
Mm-hmm. Maybe one more online.
There were actually 11 questions. I'm not
okay,
sure.
then
shall we continue, or maybe we ask the audience first?
Yeah, who wants to ask a question live here in the audience? People are shy.
Oh, there's a question in the back.
There is a question over there.
2 questions in the back.
Yes, so I would just like to connect to the previous question. So if you could do it with small models, then is it just the performance limitations that limit us to potentially in future do it in the larger ones? And does this mean that in theory we could end up with fully decidable systems at some point where we could really analyze how the big ones work as well?
So the smaller models that form liquid networks use different technology from transformers and other existing technologies. They use this physics-based way of reasoning. And I mean, in some sense, you can think of them as kind of combining models and data. And so, yeah, because of the nature of this technology, we can apply tools from the control theoretic literature. We can extract decision trees. We can do things like that. The challenge is that liquid networks require time series data. So if you have an application that does not have time series data, we don't yet have an alternative to the traditional models.
Okay, then.
There was a question, the lady in red.
Thank you for the fantastic talk. I especially like that you showed all the applications, especially in medicine, for example. So it really shows us the real impact of this technology. And this is exactly what my question is related to. So I wonder how do we actually navigate between having more societal impact than economical, for example? Because nowadays, with the widespread of AI, we see a lot of let's say, impact where a lot of maybe jobs are replaced and so on, but we do not have some applications where, so, okay, and as an example, we have some artistic jobs replaced, but we do not have a garbage removal, robot in the households, which is, I guess, economically not very attractive. So I'm just interested if you have this type of discussions also in your team with how this research is navigated.
So let's see, let me just say one word about jobs. There are tasks that we do that are repetitive and boring that the machines are good at. But a job is more than a task. Most jobs involve multiple different types of tasks. So we communicate, we interact with others, we apply expertise, we do data tasks, we do predictable physical work, we do unpredictable physical work. Not all these tasks are automatable with the technology that we have today. And so the idea is that we can offload the boring tasks to machines, and then we give more space for people to apply their expertise. And so, for instance, I've been working with people, with doctors who work on rehabilitation. And at least in the United States, a rehabilitation doctor spends more than half the time essentially going to the room of the patient, bringing the patient to the gym, and then taking the patient back to the gym. Now, imagine instead if we had a self-driving wheelchair that could just drive the patient directly to the gym, then we would have the patient and the doctor would get much more time together. And that would be good for the patient, and the doctor would be much more satisfied working with the patient than helping the patient back and forth. So you asked about the balance between economic benefits and other societal benefits. I think there is room for all of it. There is really room for broad application of technologies, and we can apply them in areas that make economic sense. We can apply them in areas that make societal sense. An important factor here is how do we get the ideas out of the research lab into the world? And for that, we really need societal level investment for societal level benefits. We really need to have, we need to be able to fund startups that are targeted not at making a lot of money in a particular sector, but startups that ensure the well-being of people, the well-being of animals, the well-being of the planet. And we haven't quite figured out how to do that yet, but I haven't lost hope. I think that it's in time that will come.
Rado wanted to ask a question.
Yes, thank you very much for the wonderful talk, Daniela. So I have a question related to the data sets. So these days we have these vision data sets like ImageNet, and more recently for robotics, people propose like videos as data sets, but they ignore forces, they ignore the touch and feel of the object. So can you say more about what you think would be the future of data sets for exploring the world around us?
Okay, let me say something about ImageNet and about benchmarks in general. So in AI and machine learning, we love to evaluate our solutions against benchmarks because that allows people to compare each other's solutions. But these benchmarks do not actually say how well you do the task. It just says, on this particular data set, how well do you do as compared to other solutions? And a few years ago, we were looking at performance, at the algorithmic performance on ImageNet. And we found that the best performing algorithms had 97% accuracy as compared to the 94% accuracy of the human eye. So how is this possible? How can an algorithm be better than the human eye? Right? It's crazy. Well, my colleagues, Josh Tenenbaum and Boris Katz, had the idea of creating a different benchmark. They created a data set called ObjectNet, where they took objects out of context. So they took your shoes and put them on the bed, and took the pots and pans and put them in the bathroom. They scrambled everything. And so guess what happened? Those 95% algorithms, they dropped in performance 40 to 50% in these newly formed data sets, which is also something that we observed in our experiments with robots. We observed that the classical solutions tend to pay attention to context rather than the task. Now, in some cases, the context is important for solving the task, but in other cases, it's not. So my first point is data sets are only as good at measuring your algorithm as the content in them. With respect to physical work, you cannot simply use video to learn or to teach a machine how to do a physical task, because the video is only visual. The video does not capture forces, that does not capture interaction, does not capture anything that any of the physicality of the information that is needed for the machine. So my own dream is that maybe someday all of our clothes will be roboticized. We will have sensors embedded in them, and all the data that is like how we move and how we explore the world, how we interact in the world will be naturally captured without us having to think too much about it. And then we can use that data to make the machines more like us. In the meantime, we don't quite have that, but in the meantime, we have bracelets and other kinds of wearable sensors that look a little bit clunky, but you can still instrument a bunch of users, collect the data from the users, and then see what we can do with that data. So Radu, I hope you and Zara are going to join us to make sense out of the data that we have collected in our kitchen.
Let's have an online question.
Sorry?
Let's have
An online question, sure.
There are plenty of questions, but maybe one practical question would be, what do you think, in your opinion, would be the first intelligent robot that can be integrated in daily life? Self-driving cars or home appliance?
Wow, so that's actually a really difficult question because, self-driving cars, yeah, okay, so I will just say that moving in the world is easier than manipulating the world. And so I know that there is a lot of enthusiasm around humanoids, but I think humanoids are really hard. And so I guess my bet will go towards autonomous driving. When we started the Toyota program that Stefan mentioned, we were always so excited to show our sponsors, look what we can do, look all the advances. And there was always the question, okay, this is very good, but what will your car do if the car drives and there's a plane landing on the highway? And we're all stumped, like always, we have no, like how, I mean, this is crazy. What would we possibly do? And so, but it's interesting because with language, my students have now began to answer that question. The work is not published, but I can tell it's under submission, but I can tell you that we can look at a video and we can see a plane landing on the highway, and we can then put it in words. This is a plane landing on the highway. And then we can use the language side of the model to reason about what to do when the plane lands on the highway, basically get out of the way. And so then you can look at the road and see whether you can turn left or right or hit the brakes or something. So so I really see that this connection between language and perception will actually enable us to do higher level, more intelligent reasoning for machines. See, in order to do a task with a robot, you actually need to have the body of the robot that is capable of doing the task and the brain that is capable of controlling the task. And in the case of navigation, when I started in robotics, the main sensor we had was the sonar. And the sonar is a very noisy sensor. right? The beam comes in and it bounces, and if you're not fully perpendicular on the surface, you're not going to measure the distance to the surface. Basically, none of the algorithms worked with robustness when that was the sensor we used. And then the laser scanner, the LiDAR, got introduced, and all of a sudden, all the algorithms that didn't work with sonar now worked with a LiDAR sensor, because the LiDAR sensor was very precise. And so that was transformational for mobility, for thinking about how robots move. And we have not cracked that problem. So we have not cracked the sensor and hardware problem for manipulators. There's a lot of efforts to think about how to make robot hands that look more like the human hands, how to build robot skin, how to do real-time connection between perception and action for interaction, but we don't have a good solution yet. And so when we'll get the equivalent of the LiDAR for robot manipulation, we all of a sudden will make a lot more progress.
Just one question to the liquid neural networks. Austria is a country that depends a lot on the SMEs. And I believe there's a lot of power in these physics-informed AI, because if you don't need that calculated power anymore, that to that extent, you do not depend on these tech giants. But my question would be, wouldn't the tech giants that invested so much in all that models and the hard and software try to block the development in this direction? So
I don't know what's happening in the big five companies. However, I will tell you that Sam Altman visited us a couple of weeks ago, and I asked him about scalability. And his answer was that scalability was the law of the world, and everything is about scalability. And he said that he continues to invest in scaling up the open AI models, and they're working now on GPT-5. And his belief is that there will be GPT-5 and maybe GPT-6, and by the time we get to GPT-6, we're done. We have learned all the facts about the world, and at that point, we can take the weights and we can bake them into a chip, and we have instant inference. Well, time will tell whether he's right, but I think that we really need to, I really believe that there is a limit to the statistical scale-up approach, and we need to try different ideas. Liquid networks is one idea, but maybe there are other important ideas. The thing is that all these, most of the solutions, most of the extraordinary performances that you see about AI today, they are due to ideas that were invented decades ago. Like we're talking 30, 40 years ago. Those ideas didn't work. Deep networks, reinforcement learning, those ideas didn't work back then. But when computing became rich and the data became rich, all of a sudden, what didn't work back then started working now. And so I believe that we need new ideas in this field, because if we don't get new ideas, then in time, everyone will be doing the same thing, and the results will get increasingly incremental. And so maybe that's another challenge to the students here. Think differently, come up with new ideas. Don't just take data and put it into standard architectures to see what happens. Try to think about a more foundational way for capturing intelligence. So my bet is on the small models that can work on SME computers and on robots, and that can be explainable and support safety critical applications. And so we'll see in time.
Is it okay if we take two more questions?
Okay.
Maybe one online, one from the live audience, and
two more questions. Great.
As a follow-up question, so could you maybe give some recommendation to the young researchers? Is it what you just said, the future or focus the AI research, for instance, these small models?
Well, I think that, so do things differently. Don't do what everyone else is doing, and ask big foundational questions. If you're embarking on a PhD, you have a few years ahead of you. So think big. Think about what would you like your thesis to be, and then walk on that path. You don't have to walk on other people's paths. We were talking earlier in a session, and one practical way to approach that is to really look at how people solve problems, look at what assumptions people make when they solve problems, and change the assumptions and see what you get. Here at the university, our objective is to uncover truth. Whatever you do that is true will contribute to the world's knowledge. And who knows how it will be helpful. You know, in the 1800s, people worked on group theory. And at the time, it was a very abstract field of mathematics. And those people in the 1800s had no idea that someday their work would be used by all of us to shop online with our credit cards, because group theory is part of the foundation of cryptography, which is enabling us to have secure online transactions.
So who will be the last one? Please, you make the pick.
Oh, I get to choose.
Yeah, please.
Oh. Okay, over there. Yeah, you had your hand up early on, so.
I have the question concerning the language. So we know I'm a social scientist, so the questions related to the culture and language. There are universal elements in the language and not universal. So the same concept is expressed by different language structure. How do you cope with this problem?
Well, right now, language is treated by foundational models statistically. So there's no notion of grammar or of common sense or of building blocks. But machine learning can be very interesting at making sense of knowledge. So I don't actually have a good answer to your question with respect to improving the way we think about structure and substructure in language models, except to tell you that we've been using these ideas to decode the language of whales. And interestingly, with machine learning, we can identify structures and substructures in a completely alien language. And so maybe those ideas would help us do better with human language. My colleague Yejin Choi, who is currently at the University of Washington, has been very active in bringing common sense reasoning into language models. And so she has some techniques for programming certain reasoning aspects of language. But it's kind of still a gap between what you can do statistically, what you can do with common sense reasoning, but you're asking about the building blocks that form the language. So here, I think we need some help from linguists.
All right. Yeah, thank you for all the questions. And now we're coming to the end, and I believe Gerti has a little
just the last word. So first of all, thank you very much. I think you really deserve a big applause. We have learned really a lot from you. And, you know, at one of your last slides, you were also saying, I mean, perhaps the future is not only in the positive way, in the sense of we have to think of how we save our democracy and what we do with our data, and if we are the product or if we pay for it. You know, it was in fall 2018 when the term digital humanism was kind of I was invented at this faculty. And there is a recent book, Introduction to Digital Humanism. And I guess you have something to read in your plane. So I would really like to provide this.
Thank you so much.
But so that you kind of remember us not only of these nasty guys who give you only books, we also have some lighter things. So a Sachertorte, perhaps it makes more sense. So thank you so much. So yeah. Thank you. And yeah, it is really hot here. As I said, already 45 years it was as hot, so nothing has changed. TU Wien is really traditional, yeah, and stable. So enjoy the get together outside. And there is, excuse me, and there is a logic launch tomorrow afternoon with Georg Gottlob starting at
4 p.m.
At 4 p.m.
So that's a Café Museum. It's an informal discussion with Sarah Kriesche from UNs will moderate, and Georg will talk about similar topics, maybe not so much about robotics, but AI and the future of artificial intelligence. So please join us tomorrow at 4 p.m. at Café Museum. And thank you very much.